differentiation rules. So we've already learned the power rule. We know it has to be sometimes rewritten in order to use it. And we just worked a nice little application. So the summary of that application is this. Never forget to remember this, that at a point of tangency, and by point we really kind of mean at a specific value of x. At a specific value of x, the function f of x and its derivative function f prime of x share two things, right? What are they? They share a y value, because they actually share an ordered pair, and they also share a what? A slope value, okay? So they have the same f value and they have the same f prime value. They share a slope and they share a y value. And again, that's kind of the nice thing about being differentiable, locally linear. If you zoomed in around a single point, you would begin to look like the tangent line itself. So here's a nice application that requires that type of knowledge. Example 9. Find the value or values. Ooh, that's what we call foreshadowing, right? Oh, could be more than one. Of k, such that the line 5x plus y equals negative 9 is tangent to the graph of f of x equals 2x squared plus kx minus 1. So it's important that you know how to do isolated skills. I know how to use the power rule. Give me a function. Let me power rule it. Okay, good. It's another thing to read a question and to have a plan of attack, a strategy for using a sequence of skills that you've learned to arrive at the answer, right? And that's really kind of, I would say, 90% of mastering the AP exam is knowing what to do and when to do it. So find the values of k. So begin with the end in mind. It's like you can work a maze backwards a lot easier than you can working forward. Have you ever done that? It's really hard going forward, but if you cheat, which is not really cheating, because I never saw in the instructions that it said you had to start anywhere. But if you work backwards, you can get to the inside a lot easier. And then you have it mapped out going forward. That's just smart, in my opinion. And that's how a lot of proofs are done too, by the way. So begin with the end in mind, and then you can plan accordingly on your goals on how to reach it. So I need to walk away from this problem with some k values in my hand, right? K values. Well, what the heck is k? K is nothing more than the coefficient of the x term in the quadratic, f of x, who has a tangent line of 5x plus y equals negative 9. So how am I going to do that? If I have an equation of a tangent line and I have an equation of a function, why would I set them equal to each other? They have the same y value. So when we set them equal to each other, we have to be careful. In Algebra 2, pretty much every single equation that was ever handed to you was handed to you y equals already, right? So that's why you could just set them equal to each other. This one is not really equal to y just yet. So let's solve this one for y, and we get negative 5x minus 9. And then we have the equation over here, which I'll call y instead of f of x. It's 2x squared plus kx minus 1. Good. So, ooh, I sure did. Thank you. Thank you, kx. And so because they have the same y value there, now I can set them equal to each other. So I'm going to go ahead and label what we're doing here. Just kind of thinking that maybe this is a free response question. And anything you could do to communicate your work more effectively, feel free to do it. So I know that negative 5x minus 9, at whatever value of x it is, has to equal 2x squared plus kx minus 1. Now you did learn in Algebra 2 that if you have two unknowns, which we do, right? We have x and k. You need how many equations to find a unique solution? 2. We have one equation with two unknowns. Darn it, how are we going to get another one? Derivative, right? Yeah. Slopes. They have the same slope there as well. So now, let me with notability. Hello?
It's the iPad of mine. I was trying to find it.
Oh.
It was in my car.
Oh, okay. But it's here now? Oh, it was a latent ping.
Yeah.
Oh, okay. I was going to say, does it know that you found it? It's okay. I got it. So let's go ahead and find the derivative of the tangent line. What's the derivative of negative 5x minus 9? Negative 5. And that makes total sense because a line has a constant slope and it's mx plus b. So you could have actually found the slope without sweating it out using the power rule, right? Ooh, save some calories there. And this one, y prime would equal what? 4x to the first plus k minus 0, where k is a constant, right? Our favorite kind of constant. Double k, double k. Is that too many k's? All right. So now that we know that the derivative functions, we can set the slopes equal to each other. And we got negative 5 has to equal 4x plus k. And there's our second equation with two unknowns. So now what? Now the fun begins. Yeah, there's a lot of methods. I would probably choose substitution here as opposed to linear combinations or elimination, as y'all called it, because this one here is easy to solve for k. So k would equal negative 5 minus 4x. And then that one, you remember, is set up, ready to find ultimately what I needed to find, right? The question wanted me to walk away with a k value. And the way that a lot of these questions are sometimes set up is they set them up in such a way that you're actually encouraged to find the other variable first. And of course, if you lose sight of what it is you're supposed to walk away with, you can get exhausted at the end and be like, I have a solution, it must be the right answer. And guess what's sitting there usually right there on the multiple choice is A, that wrong answer. I'll show you what I mean. If I solve that for k, it's a lot easier. So that means now I'm going to plug that in right over here to the other equation for k. Yeah. Well, if I do, it'd be like multiplying both sides by negative 1, and I would have negative k equals positive 5 plus 4k. Because you don't like them both being negative? Oh, sure, absolutely. Yeah, you can rearrange any of those terms, and the sides can be flipped. That doesn't matter. All right, so let's go ahead and plug in. So, negative 5x minus 9 equals 2x squared plus parentheses for k, negative 5 minus 4x minus 1. And now we have one equation. Oops, I forgot an x. Yep, hasty make wasty. I just caught that. There we go. Now I can solve. So I expand it out. Negative 5x minus 9 equals 2x squared. Distributing the x from the right-hand side. That's kind of fun. Negative 5x. Thanks for your help today. Minus 4x squared. I already made a couple of careless mistakes. And now we have a squared term, a non-squared term, and a constant. So it's algebra 2 all day long. Get everything on one side. Set it equal to 0. Yeah. So let's go ahead and combine like terms. My daughter is learning like algebraic skills right now, and her teacher tells her to combine like terms on one side first. So let's do what the 8th grade algebra teacher tells us, because that's a good algorithm to follow. So we'll combine the 2x, and of course you can do some of that in your head. Now at this point, strategy-wise, I would probably collect everything on which side. The right side has more terms, but I would still get it on the left just because, yeah, we kind of like our first term to be positive. So positive 2x squared. And then what happens with your negative 5x's? They cancel. That's sweet. And then I bring the 1 across, and I get negative 9 plus 1, which is negative 8. And now that equals 0. So hopefully those maneuvering of terms is pretty easy for you at this point. Now, when it's equal to 0, we factor it, or we can separate the variables, however you want. Yeah. If you want, because there's only one variable, you can actually separate, divide through, and then when you take the square root, you have to do what? Plus or minus, so plus or minus 2. This one, not all of them do this, but this one also you could solve by factoring, and when you factor it, multiplies or it factors into the product of two conjugates, and you're less likely to forget plus or minus, because some people forget plus or minus still when they extract square roots. Okay, so guess what? If this were a test question, answer choice A might be positive 2, answer choice B might be negative 2. Are either one of those necessarily our answer? Nope, because we were interested in K. So this is where substitution is kind of nice. Substitution is already set up then to find that other variable with an explicit equation. So K equals either negative 5 minus 4 times negative 2, or K would equal negative 5 minus 4 times positive 2. So let's see what that gives us. That means that K would equal 8 minus 5, which is 3, or K would equal negative 8 minus 5, which is negative 13. So there are two values that actually work. Okay, two values that work. Now, how would we make sense of those solutions? Well, let's come back up here and see. That means f of x could either equal 2x squared plus 3x minus 1, or 2x squared minus 13x plus 1. And if you remember from Algebra 2, the linear term in a quadratic, if you were to complete the square, is responsible for the horizontal shifting of the graph. Both of those parabolas, whatever they're going to end up being, would be tangent to this line, y equals negative 5x minus 9. Now, we did all that without having a visual understanding of what we were doing, and we did arrive at the right answer. But sometimes it's nice to make sense of what we did. And rather than having to sketch it all by hand, if you just scroll down, I have them for you. So notice this line is the same line in both pictures. It's the exact same line. But what's different is the parabola, right? This one over here is tangent to it at negative 2. And this one over here is tangent to it at positive 2. So we basically just kind of slid this down and made another tangent point. And that's it. So there were two solutions, and we found them. Neato mosquito. Multiple step problem. They get kind of fun, right? But you always begin with the end in mind and work backwards. What do I need to get what it's asking me to find? If this were a free response question, though, it would probably be broken down into some smaller things, like it's A, B, and C. Like it might ask you to find the derivatives or something like that. But not necessarily. All right, so that's a good one. I like that one. I like those fun problems that are fun, that make you think. Because they're fun. Yeah, thinking's fun. Was this one easy? Sure. So this would be one of those fun-easy problems. Fun-easy. Both fun and easy. Okay, so here we go. The sine and cosine rules. Sine and cosine. Yeah, the power rule does not work on sine and cosine. So you need a separate rule for the derivative of sine and cosine. And get this, appropriately enough, they're called the sine and cosine rules. Nice. So here's what the sine and cosine rules say individually. The derivative with respect to x of sine is cosine. So what's the derivative of sine? Cosine. That's cool, because if you want to know how fast the sine graph is changing at any value of x, it's just the cosine value at that point. And they're co-functions of each other. Interesting. The derivative of cosine is almost as easy. The derivative of cosine is not positive sine, but rather negative sine. Yeah. You remember cosine? He was the selfish one. Cosine, cosine, me. And then he always changed the sign and the identity. Cosine is negative. Cosine becomes negative. Now, here's an easy way to keep them straight. They are each other's derivatives, except cosine is negative, and it turns out that the derivative of any function this year that starts with co, whether it's cosine, cotangent, cosecant, or later on arc cosine, arc cotangent, or arc cosecant, also known as inverse cosecant, they're all going to be negative. They're all negative, and all the other ones that are not co are all going to be positive. So that's an easy way to keep them straight from the beginning. So do you want to prove that? Do you want to prove that? We already did. We did. We actually proved the sine one. I think one of these was in your worksheet on 1.4. I gave you the hint for the composite identity, and the other one we did in class. So you would have to expand it using the composite identity and group it together, and you can get the results. So I'm not going to prove that again, but it does work. So now that we have those memorized, look what we can do. We're building up rules. We have the power rule now, and we have the sine and cosine rule. And if you update notability, there's more flavors. And I haven't done it yet, but apparently you could draw a straight line and long hold on the end, and it snaps to a straight line. So I'm really liking that for tangent line purposes. I'm so excited too. I'm going to download it, maybe over lunch. Okay, here we go. Find the derivatives of the following. Y equals 2 sine of x plus 7. Do any terms need to be rewritten? No, we're ready to go. So what's the derivative of the left with respect to x? Y prime or dy dx. Good. And what's the derivative of 2 times sine? 2 times cosine. Yeah. Constant multiples go along for the ride. We had that little rule earlier. And then plus the derivative of 7? 0. 7 doesn't change. So there you go. That's it. That's easy. Wow. Letter B. Letter B. Okay. What's the derivative of the left side? F prime of x. And now we have 2 terms. Oh, so remember, each term we can treat as a separate individual problem. What's the derivative of x? 1? Minus sine of x. God, y'all are good. It's easy. So that was a combination of 2 rules, wasn't it? That was the power rule and the cosine rule. Nice. Oh, I know. I'm excited. My tangent lines. You talk about kissing the curve before. They're actually pretty good still, but look, they got a little bend right there. But man, it's going to be perfect now. A lot of kissing going on. It will be straight line graphs. Maybe there's like a parabola where you curve like and you hold it and it makes it into a perfect parabola. I don't know. We'll see. It doesn't. You already tried it. Okay. How about this one? I love this one. We have g of x equals 2, which is a constant multiple, times sine of x halves. Is that plus? No, that's times cosine of x halves. Uh-oh. We have a variable function times a variable function. We have a product of two variable functions. Can we use the sine and cosine rule on that? Do you think it's just the derivative of this times the derivative of that? No. So that's one problem we're facing. Notice we also have x halves on the inside. That's not just plain old x. So we have a composite function, and we have a product of two composite functions. This is later going to require the product rule and the chain rule, but we don't know either of those yet. So right now, if all we have is a hammer, I guess, and a screwdriver, we got to make everything look like a nail or a screw, right? I guess the hammer would be the power rule, and the screwdriver would be a sine and cosine rule. So we don't have a product rule yet or a chain rule. So how do I manipulate that into either a plain old sine with a plain old angle or a plain old cosine with a plain old angle? Come on, you can do it. Well, here's the thing. If I multiply by 2, I got to do it on both sides. Now I have 2g of x equal that. Plus, I can't distribute the 2 inside the angles. The only way I can change the angles is by way of identities. And I need to change those to an x. You can do it.
Can you plug it in x?
No.
Oh, that's...
Yes. Yes. That's the double angle identity for sine. You need to know it. There it is. Sine of 2 times an angle is equal to 2 times sine of the angle times cosine of the angle. And the other one you need to know is cosine of 2x. That one's a little bit easier to remember because it's like the bizarro Papa Pig. It's cosine squared, not plus sine squared, but cosine squared minus sine squared. Yeah. You need to know those. Okay? So, notice what we could do. G of x then could be equivalently written. If I have 2 sine of blob, and I'll use blob a lot, times cosine of blob, we'll look up here in the identity. 2 sine of blob is equal to 2 sine of blob. So I'm going from right to left. So in this picture here, my x is really a what? An x halves. So when I go from the expanded to the condensed, what do I need to do with my angle x? I need to double it, right? So this is going to become just plain old sine of twice x halves. And what's twice x halves? X. OMG. Oh my gosh. What? That was just equal to plain old sine of x. That's a pretty dang good costume, right? I didn't recognize him. But notice I called it what? Did I call it G prime? That was still G. So now we could call him G prime, and of course he's what? He's cosine of x. Which if we want to put him back in half angle happy land, that would be cosine squared of what? X halves minus sine squared of x halves. Would that work? Sure. You just agreeing with me? Or you validated it? Yeah, if you look what we did here, this x is a variable. So whatever x is here in the top, when I condense it down to sine of an angle, it's going to be sine of twice whatever that angle is. So what's twice x halves? Plain old x. Yeah. And now I did it the other way around. Cosine of x, I can let that become x halves. By the same token, if you're going from left to right, you take half the angle. If you're going right to left, you double it. So now would you have to put it back in this cosine squared minus sine squared? Probably not, no. The answer would probably be just cosine, okay? So you're learning strategies as we go, right? We know that we sometimes have to rewrite in order to use the power rule. But identities are still very, very useful for becoming mathematical synonyms and giving us something we can actually work with. And speaking of all that work, it's kind of made me hungry. So let's take a lunch break. Of course, I don't eat lunch, so I'm just saying that for the film. Oh, my goodness. I need to download it.